Please, if I'm moving fast, you humbly alert me. So where were we? We are talking about force on a current conductor. So I've already explained what all these are about. We are saying that when current is passed through a wire, you know, a wire is a conductor. There's the generation of magnetic field. That's basically what it means. Or a magnetic field is established in the presence of current passing through the wire. And as a result, when you bring a magnet, an already magnetized material near it or a magnet near it, the wires will tend to move sometimes in the direction of it, based on the direction this thing, this we're showing it. Basically, that's what it means. Now, if the magnet is placed in such a way that its field is parallel to the length of the wire remains still. So when the magnet is normally placed in such a way that the field of the magnet is parallel to that of the wire, parallel to the length of the wire. It's parallel to the length of the wire. Then I say that the wire remains still. And so when it is positioned in such a way that the field of the magnet is parallel to the length of the wire, then we are seeing that the wire remains still when the current is passed through it. That's showing that no force acts on it. Normally when they are parallel, then they show that there's no force that acts on it when the length is parallel to the magnetic field. So when the length is parallel to the magnetic field, basically there's no force acting on it. There's normally no force acting on it when the length is parallel to the magnetic field. Now, we are going to consider something called Fleming's left-hand rule. Fleming's left-hand rule. And this is going to tell us a lot of things. Basically, when we are talking about the force on a conductor, and so it has been grouped into, or it has been simplified into a law, which we call the Fleming's left-hand rule. And this, when you're asked to quote it, you would have to quote it verbatim. I mean, you would have to quote it quote unquote. You wouldn't have to paraphrase it because it's a law. So please, you take notes. Now, we are going to consider the Fleming's left-hand rule. I know you all might have heard of Fleming's left-hand rule. How many of us have heard of the name before? Fleming's left-hand rule. Fleming's left-hand rule. Now, the Fleming's left-hand rule states that I'm quoting it. It states that if we stretch out the thumb, if you stretch out if we stretch out the thumb and the first two fingers of the left hand, so if you stretch, when we stretch the thumb and the first two fingers, so these are the first two fingers. This is my first finger. This is my first finger. This is the second finger. So if you stretch out the thumb, so this is my thumb. I hope you cannot see. This is my thumb. This is my thumb. And the first two fingers, and these are my first two fingers. And the first two fingers of the left hand, this is my left hand, so that they are all perpendicular to each other. And so when we say perpendicular, that means this is perpendicular, one is perpendicular to one. And so let's say when I have this, so this is perpendicular to this one, the first one, so that they are all perpendicular to each other. And we point the second finger in the direction of a conventional current. And so that means you are pointing this second finger, if you have something like this, I'm just going to explain it. Then we point this one in the direction of a conventional current. When we say conventional current moving from positive to negative. We point this one to the current, conventional current. Then we point the forefinger. This one is the forefinger in the direction of the magnetic field. Then that means this one moves in the direction of the magnetic field. Then, which is the north to south. Then we point this thumb. This is the thumb. We point this thumb. We point the thumb in the direction of the motion for the perpendicular, for producing the motion. So this one moves in the direction of the motion. Now, in simple terms, it means that when a conductor is connected in what do you call it? when a conductor, so this one is not part. This one is not part. We are talking about this. We are talking about a current in a distance. So when it is passed through a current, then definitely we are going to have one moving. When a current moves, then definitely there's going to be a current generation. And when a current is generation, it happens what they call it in a motion form. That's what it means. And so when you put a conductor, or when a conductor is passed through a current, when a conductor is passed through a current, we are just simply meaning that definitely there will be the generation of conventional current, which would have to move from positive to negative. And when that happens, it creates a magnetic field. And when it creates a magnetic field, because before it created a magnetic field, there was something, there's a motion. And so that is it, the motion of the particles moving, and that's generating a current. And so it means that in that sense, we have three main things we are going to consider here. We are going to consider the field, the magnetic field, which is generated as a result of the current being passed. And we're also going to talk about the motion, which enables the movement. And we're also going to talk about the current, which is generated, which causes the magnetic field. And so I'll read the Fleming's, and it has all been grouped, or it has all been spoke about in what do you call it, or it has all been coined into.
This is dark. We cannot see. I cannot see.
You cannot see my hand. Can you see my hand? Can you see
Yeah,
my?
we can see.
So
Yes.
this one, when I say that, so according to the Fleming's left-hand rule, it's saying that if you stretch out your thumb and the first two fingers, so these are the first two fingers, and there's my thumb. Now, when you do that, the Fleming's left-hand rule says that this one is pointing in the direction of this, and this must be perpendicular, but this one is pointing, the thumb is pointing in the direction of the conventional, sorry, the thumb is pointing in the direction of the motion. This one is pointing in the direction of the conventional current, this one, and this one is pointing in the direction of the magnetic field. That's what it means. So it means that there's supposed to be a certain motion, and there's supposed to be a certain current, and the current moves in motion, definitely. And when the current moves in motion, definitely there should be a certain, what do you call it, magnetic field, which is generated. So these are the three main things when we are talking about a force on a conductor, and we are going to express them mathematically. So I'll reiterate the law so that if you want to write, you write. Fleming's left-hand rule states that if we stretch out the thumb and the first two fingers of the left hand so that they are all perpendicular to each other. Sorry, baby girl. Fleming's left-hand rule states that if we stretch out the thumb, so if you stretch out the thumb and the first two fingers of the left hand, so it should be the left hand, so this is my left hand. To you it seems like right, but this is my left hand. So that they are all perpendicular to each other. So they should be perpendicular to each other. So this is perpendicular to this. So that they're perpendicular to each other. And we point the second finger in the direction of a conventional current. And we point the second finger in the direction of a conventional current. And we point this thing in the direction of a conventional current. Conventional current. A conventional current, you can write into bracket positive to negative. You can write into bracket positive to negative. And we point the forefinger. This is the forefinger, or the first finger. And we point the forefinger in the direction of the magnetic field. We point the forefinger in the direction of a magnetic field. We point the forefinger in the direction of a magnetic field. We point the forefinger in the direction of a magnetic field. The direction of a magnetic field. The direction of magnetic field. That is north to south. North to south. The direction of the magnetic field, north to south. Then the thumb will point in the direction of the motion. The thumb will point in the direction of the motion. The thumb will point in the direction of the motion. I wish I could draw it, but I've already explained it. The thumb will point in the direction of the motion. You can write into brackets or force producing the motion. So the thumb will move in the direction of the force producing the motion, or the motion. So now, so let's talk about the force on a conductor. So when a conductor is placed in a magnetic field or a current is passed through a conductor, let's consider the force on the conductor. And we are going to consider this using the Fleming's left-hand rule. Now we are saying that if the conductor makes an angle of theta with a magnetic field. So if the conductor makes an angle of theta with a magnetic field, then number one, so we are considering a conductor, which is a wire or anything, makes an angle with a magnetic field. Then number one, we are saying that the force is proportional to sine theta. We are saying that the force is proportional to sine theta. So number one, we are saying that force is proportional. Proportional means, you know the proportionality sign. It's proportional to sine this thing. Proportional to sine. It's proportional to sine theta. Up to sine theta. I can just write it. It's theta, and please. Let me just write. Oh, proportional to sine theta. Then number two, we are saying that the force is proportional to the current passing through the conductor. So the magnitude of the force is proportional to the current passing through the conductor. So we are saying that F is proportional to the current, which is denoted by I. Proportional to the current passing through the conductor. And number three, we are also saying that the force is proportional to the flux density. The force is proportional to the flux density. Sorry. So number one, we are saying that the force is proportional to sine 30. That is if the conductor makes an angle of theta with the magnetic field. So we are saying that force is proportional to sine theta. And number two, we are saying that force is proportional to the current passing through it. Number three, we are saying the force is proportional to the flux density, which is B. You know the flux density. The number of flux or the number of lines in an area per area. Let me put it that way. Number four, the force is proportional to the length of the conductor. So the force is proportional to the length of the conductor. So the force is proportional to the length of the conductor. Length of the conductor. The length of the conductor. So that is it. So we have something like this. Now we have our first, let's say this equation 1, equation 2, equation 3, equation 4. Then now we can equate them, or we can say we can add all of them, or we can sum them, all of them up, or we can combine them. That's what I want to use. We can combine them. So there's it. So for instance, we know that mathematically we know that force is equal to sine theta. That's what you mean, or proportional sine theta. It's also proportional to this, and proportional to this. So then we can say that force is proportional to the product, is proportional to B. Force is proportional to B. Force is proportional to I. Force is proportional to L. And also that, I think that is it. And also sine theta. Also sine this. So combine all of this, you can see force is proportional to all of this. So however, we can say that force is equal to K B I L sine this theta. So that is it. So we are saying that force is on a conductor. Number one is proportional to the sine theta. That means the angle between the magnetic field and the conductor, or the angle that makes the conductor mix with the magnetic field. We are seeing that force is also proportional to the current passing through the conductor, and it is also proportional to what do you call it, the magnetic flux density, and also proportional to the length of the conductor. So we can combine all of them. We can combine all of them and put them into one equation. Now, so the SI unit for B, we know is Tesla, and which is equal to Weber per meter square. Now, 1 Tesla may be defined as the flux density. So we can say that where we know that K is a constant, already we know that. So when K is equal to 1, F is equal to Bell sine theta. It's theta, please. So let's take note. I'm coming. Some people are. That is it. So, so for instance, when the angle made is 90, when the angle made is 90, then we are saying that sine 90 is what? What angle? When the angle made is equal to 90, then we are going to get the force to be F is 1. So if K is 1 to so that's what we are going to get. F is equal to Bell. F is equal to Bell. So that's it. When K is equal to 1. So when the angle placed this is what do you call it? It's 90 degrees, then F becomes, or F is equal to, yeah, Ruben, talk to me.
So please, is the 90 degrees constant to every equation?
No, that's why I said that if the current, that's why I said if. Are you getting it? That's why I said if the current.
Yes.
Are you there?
Yes, sir.
So the current can be anything. That is why we said sine theta. So that means if the current, if the angle is 90 degrees, then that means sine will be equal to, force will be equal to Bill IL, considering the constant being equal to 1. So F will be going to be Bill. And when it is equal to another angle, then that means the angle it will play. You write the distance as Bill sine theta. That's what you are going to write. Then you substitute the angle in it.
So say when a question is asked and they don't mention any angle, that means we accept it to be the angle to be 90.
So when a question, definitely the question would have to tell you that if there's an angle or not. If there's no angle, then that means you won't even consider the angle. That means the sign won't be there. That means the question it didn't make any angle, or there wasn't any angle between the conductor and the magnetic field. So as a result, you won't consider the angle. So it will be force is equal to Bell. Are you getting it? Now, when the question also says that maybe the angle,
yes, sir.
When the question also says that the conductor was perpendicular to the magnetic field. The conductor was perpendicular to the magnetic field. Then that means if it's perpendicular, then that means the angle made was 90. Are you there?
Yes, sir.
So then you can do it. So normally they put it in. Listen, let me give you an example. So for instance, so when you have something like this, let's say this constitutes the magnetic field. Let's consider magnetic field. Now, so let's say we have our conductor. So we can place, let's say we can place our conductor here. Now, when we place our conductor here, then we want to consider the angle that you realize that this conductor will make an angle with this magnetic field. I hope you get, And mathematically, the angle here will definitely be the same as the angle here. And so if the angle is making, if the conductor is making an angle with this magnetic field, and that means when we are calculating, we are going to consider the angle here. However, if the conductor is placed parallel parallel to the magnetic field, and that means it is not making any angle. Are we getting it? Or if the conductor is parallel to the magnetic field lines, then that means there's no angle made. That's what it means. On the other hand, if this thing is placed like this, if the conductor is positioned in such a way that it is perpendicular to the magnetic field, then definitely you know that the angle will be here or can be here, any way you want to consider it. Then that means the angle here is 90 degrees, and so here will become 90 degrees. Then according to this, we are considering the magnetic field, and this is the magnetic field. And the magnetic field, we are considering a certain area, and so the number of lines represented in the area constitute that of the magnetic flux density. That's why we have the B here, and that would tell us the strength or the force of the distance on the conductor. And the length would also have a what do you call it? A part to play. And so this will be the length of the. This is the length. So the length of the conductor is also given by L. Length of conductor is also given by L, and that's where we had this. And the current passing through the conductor is what we call this. That's the I. I hope you are getting it. Please, I hope you're getting it.
Yes, sir.
Good. Yes.
Good. So let's also consider. So immediately when it is 99, definitely you know that your angle is 0. So your angle, the sign 90 is 1. So then we are going to use F is equal to Bell. F is equal to Bell. So let me just put this one inside so that you know that it's 90 degrees. That's it. Now let's consider magnetic field of current carrying. Now magnetic field of a current carrying wire or conductor. Magnetic field of a current carrying wire or conductor. We are going to consider that one too. Can I please erase it? Can I please erase it? Remind me more.
No.
Can I?
No.
No. Okay, I'm waiting for you. Next year by now, you guys will be writing. So it's just around the corner. So study hard.
So next 2 years.
I want to inform. Which one are you?
1. Form 1.
Oh, okay. The form 2 is next 2 years. Next year. Can I please clean it? So write it and let me do it, please. So after the lesson, the class, the private classes for you PM me so that they talk. So that is it. So, okay, I hope now I can erase it. Won't you mind me small?
Yes, sir.
Yes.
So we have something like this. Yeah, considering. I want to draw. Now when you have a magnetic field of current carrying wire, that means a wire carrying current. I don't know how to put it. A magnetic field of a current carrying wire or conductor. This I've already explained it, so there's no need to. Now let's consider the force between two parallel current carrying conductors. That means if you have two parallel current carrying conductors, that means if you have one here and one here and they are parallel. If two conductors carrying current are placed parallel and near to each other, that means when they are placed parallel and they are near to each other, that's what happens. Now, to each other conductor will experience the effect of field of the other. So they'll both experience field on each other, or a force or some attraction on each other. Let me put it that way. And so, for instance, if I have so when we have something like this too. As for the form 2 that I call for adult second graduate.
Hey, sir, what have we done? Sir,
Oh,
what have we done?
I was just asking. I was just asking.
Yes.
God bless that man. Oh.
Like you know.
God bless him. I'm not an MPP, but at least some people couldn't have gone to school, but for the free SHS, I think.
He will be tall. He will be tall next.
Aputo. So
yeah.
Now, if you have, is it Tina who is talking? I'm drawing everything for you so that you can appreciate. Oh, before.
Say you will be tall next year.
Who will be tall next year?
Say no. You will be tall. Tell you that we are here. You will see.
Oh, 76 years. Oh, he's waiting for his death. No, you are talking about height.
Say.
Yes. So now let's continue. So if you have two parallel connectors, carrying current connectors, we
That
are
means
just trying
tomorrow
to
is
say
my
that
birthday. That tomorrow is my birthday.
when you finish PME.
Okay.
Okay, so when you have two connectors carrying current, so this we assume that these are the two connectors and they are all carrying current and are placed parallel. You don't realize that they are placed parallel. That means they have the same distance. That's it. So they are placed parallel. Now, this is the magnetic field around both of them. We assume that this will have an effect on this, whilst this will also have an effect on this. That's what we assume. Now, the conductors will either repel or attract. So the effect you are talking about is either the conductors either repel or attract, because don't forget that they are all magnetic, because they are all carrying current. So as a result, they all carry a certain magnetism in it or magnetic field around themselves. So it is either but they are parallel. That is one issue. So it is either they repel or they attract. Now, the conductors will either repel or attract each other depending on the direction of the current in the conductors. And so they will repel depending on the direction of the current in the conductors. Now, according to Ampere, who is a scientist who propounded all this, according to Ampere stated that the parallel conductors attract each other when the current in them flow in the same direction. So realize that when the current is flowing in the same direction, so we assume that there is a current flowing. Now, when the current is flowing in the same direction, then we are saying that these two will attract. Now, but it will repel when the current flows in opposite direction. So this means that when the currents are flowing in opposite directions, these things will repel. They won't attract, it will repel. So these arrows will point to this side, this will point to this side. But because the currents are moving in the same directions, you realize the current around this is moving in this direction, and the one around this is also moving in this direction. So we can say the current is moving in equal direction. And so as a result, they are going to attract. However, if the currents are moving in different directions, now let me draw a typical. Are you done drawing this, please? Are you done drawing this, please?
No.
Please, if you are drawing, draw it. Let me also explain that one. Have some 3 minutes more. Oh, we have commerce tomorrow or elective mass. It's elective mass. Okay, we have elective mass tomorrow, God willing. This month, yeah, please, yeah, busy. We are serious studying, so we want everyone to partake in the class. When you put every work on the distance, you should partake. There is one of later evenings. I don't mind you guys. Is that when you even put a question there, people don't attempt. They don't even look at the questions. Really, they see the question. You hear chill. I've been hearing it in my ears. Chill. I lie. Especially Tina and Harriet and Daniela. Yeah. So now I don't even want
That's
to.
a lie. That's
It's a
a
lie.
lie.
Mate.
Yes.
Hey, say why?
So I don't even want to worry myself to put it on a platform, because initially I was doing that, but when you put it on a platform, a few people solve it. I think Thelma and 1 or 2 people. The rest, they don't solve it. They want me to come and beg them. So me there. But
Yes, but I need to beg.
You said
Can you say anything?
I dream bonnet girl.
I'm talking to my mother.
Yes, so I expect that if I put on the platform, like after learning today, at least I can get some questions. Initially, that was what I was doing. I was just looking for past questions on every topic we learn. Then I put it on the platform in the evenings so that we all go through it. But you go, Otoro, they won't even mind you. Maybe they say, I've been hearing to my listening. That's all of late. I don't put it there. I hope what I'm saying, I'm not lying. It's true, pa.
So you start this one, you do.
So when the currents are moving in different opposite directions, you realize that here the currents are moving in different directions. And when that happens, then we are saying that the conductors which are parallel, they will repel. Instead of attracting, they will repel. But when the current is moving in equal direction, they will attract. Should we do some more time or we should close? We are tired. Because our class will end very soon. Should we do some extended time or we should close? We are tired. For my me,
Sir, you decide.
is it?
You decide.
I can't hear you. Well, the class will end very soon. I'll upload everything on YouTube so that those who couldn't listen, you can go on listen. But next time we are talking about motion of a charged particle in a magnetic field. Motion of a charged particle in a magnetic field. Please do the private class will go. PM me. God bless you so much. You are not my me, so I presume you are closing.
Say.
Yes.
Say.
Yes.
Say me, I think we should close,
Okay.
so that you
Tomorrow we
put
continue. God bless
questions
you.
on
God
the
bless you.
platform. We solve.
Is that?
Amen.
Oh, yeah, so
I said, so that you post questions